Bohr model reading. Wow, there's so many models up in here. I mean, there's me. There's all the atoms. We could make a TV show. Chemistry's next top model. I mean, I'd win, but whatever. Alright, so let's see. What's it say? It says, take a moment to examine the data and annotate your thoughts on the table. Well, first off, I'm thinking this is slanted. What the hell? Okay, what next? What I'm saying? I've got different colors: red, orange, green, blah blah blah. And then I've got these different chemicals: lithium nitrate, lithium chloride, lithium sulfate. So these ones are all lithium, basically, and they're all red. What about these ones? Calcium nitrate, calcium chloride. Okay, it's again calcium, and they're orange. Sodium. Okay, so basically, whatever this one is in all of them, is what I'm noticing. Ooh, pink lilac. Pretty. What patterns do I notice? So I noticed color with, I don't know what to call these. Bottom elements, maybe? I don't know. With elements on bottom. Notice that each metal atom, and so on, is associated with a specific flame color. Okay, so these are metals. So elements on bottom, color was with the metal. Lithium compounds all make a red flame. Yeah. Well, the barium compounds all make a green flame. Do they? Oh, yeah. Barium all make a green flame. The other atoms in these compounds do not seem to affect the color of the compound. So CaSO4, CaCl2, CaNO32 all have the same color flame, but CaCl2 and NaCl do not. Right? So the Cl doesn't affect flame color anyway. So the metal atom must be responsible. Alright, so because of this, chemists often use the flame test to quickly confirm the presence of certain metal atoms. Makes sense. If it burns red, you've got lithium. For example, a chemist can recognize the presence of potassium. Oh, I was just saying this. In any compound because it will burn pink lilac. These flame tests are also the basis for the colorful flames in modern-day fireworks. Ooh. If a firework should burn red, for example, then it should include lithium atoms. Okay, so if I wanted to make a green, blue-green, I'd put barium and I'd put copper. Interesting. Why do different atoms produce different colors of light when they are burned? I don't know. What is causing the light? What's causing its color to differ from atom to atom? Scientists puzzled over these questions for hundreds of years. Yeah, I don't know either. That's weird. In 1913, Niels Bohr created a model of the atom, so many models, to explain why each type of atom produced a different color of light. Okay, so he's got an idea. He began by studying the hydrogen atom H, since it was the simplest atom with only one proton, one electron. No neutrons? I guess that is simple. You can't get much more simple than that. Bohr reasoned that the electron can orbit around the nucleus at different distances, like planets orbiting the sun. Right? So I guess instead of gravity, you'd have electromagnetic force, but still you'd get a force keeping them in orbit. Each orbit is called a shell. The electron, oh, so I'm looking down here. So these are shells, I guess. That caught my eye because I'm noticing it's orbits, right? So I have 1, 2, 3, 4 shells. The electron has a different amount of energy depending on what shell it's in. A low energy electron will be close to the nucleus. High energy electron will orbit farther from the nucleus. Okay, let's capture this. So orbits equal shells, and then far shells equal high energy. Close shells equal low energy. When an atom is heated, the electrons absorb the heat energy. Okay, hold on. So they're going to go to the far shells and move farther away. Oh, yeah! These electrons are said to be excited. I'm excited. Well, I mean, if you think about like a little kid excited, right? They have energy. When an electron falls from an outer to an inner shell, so they're going high energy to low energy, it releases the extra energy in the form of light. Those are the colors. The color of the light given off depends on the energies of the two shells. What changes from atom to atom and shell to shell? So a different atom has different shells, I guess. This is why each atom releases different color light. So let's look at this. So we start at 1. So it says excited electron moves away from nucleus. So this is with heat. And then 2, electron moves back. It releases energy. So when it goes back, we've got light. So like the red or the green or whatever. How to draw a Bohr model of the atom. In the Bohr model, different shells, or energy levels, hold different amounts of electrons. Interesting. Start from the shell closest to the nucleus, in the middle, and go outward when filling the electrons. The electrons on the last shell, farthest from the nucleus, are called valence electrons. So valence are the outer last shell electrons. So first shell can hold 2, second can hold 8, third 8. So here hydrogen. It only has 1, so it has 1. Okay, so lithium, the first can only hold 2. Hold 2, so it adds the third one out here. Same thing here. The second has 8, so the third one. And then the third one has 8, so the fourth one has to go outside. Hey, you know, something interesting? These each only have 1 on the outside. So their valence electron, they all have the same number of valence electron. That's kind of interesting. But I mean, obviously very different, right? Like this one, it's a lot bigger. Okay, so I know what valence electrons are. I know what the Bohr model is. I know how to draw them. I know why different lights. I know so many things. Wow, learning is so great.